Alright, so here we are with Unit 7, Lesson number 2, and we're going to look at two things, solubility factors and um, things that affect the solubility. So let's take a look first at the term solubility. Solubility is the amount of solute that will dissolve in a solvent. So if a lot of a solute dissolves in a solvent, we say that that material is very soluble, it has a high solubility. One of the things that determines solubility is what we call the nature of the solute and the solvent, and we already talked about that. That is that phrase like dissolves like, which means anything that is polar is going to dissolve pretty well in water, but anything that is nonpolar is not going to dissolve um, in water because they are opposites of each other. So if you take a look at, and I'll write down an example, I'll give you an example of a couple of substances that, for example, would not dissolve in water. So, for example, if you take the substance iodine, the element iodine is one of our Brinkelhoffs, right? And because there are two of the same atoms bonded together, and if you did the lines of symmetry, there's one line of symmetry, there's two lines of symmetry. So there's at least two lines of symmetry, which means this is non-polar molecule. And that means that this will not dissolve in water, because water will only dissolve things that are either polar or ionic, and that's what this phrase is referring to. And I'm not going to show the video because it's a pretty long video. So if you take a look at this, if you take a nonpolar solute and a nonpolar solvent, they will dissolve. If you take a polar solute in a nonpolar solvent, remember, like dissolves like, that's not going to work. Ionic in a nonpolar solvent will also not work. I'll give you an example actually of a nonpolar solvent, because since it doesn't seem to be. For example, a nonpolar solvent would be CCl4. CCl4 looks like this. It has a carbon at the center and then Cl's around it. The lines of symmetry, of course, would make this a nonpolar solvent. So this would be the example of a nonpolar solvent. Carbon tetrachloride happens to be a liquid. So this, the iodine, would dissolve in the carbon tetrachloride, but it's not going to dissolve in water. And I think I wouldn't worry about this chart as long as you understand what this phrase means. I think you're in pretty good shape. Second thing is temperature. How does temperature affect solubility? Well, of course, you've probably seen this in real life. If you take a sample of iced tea and try to dissolve sugar in it, you notice that a lot of times the sugar sits at the bottom, and no matter how much you stir, it never dissolves. It'll only dissolve a little bit of it. So temperature does affect solubility, and basically the higher the temperature, if you increase the temperature, you increase the solubility, meaning the warmer the water is, the more solute will dissolve in it. So of course, hot tea will dissolve more solute than cold tea would, iced tea. Now, and that's with solids. Here's the problem you run into, is that gases are actually the opposite. When you increase the temperature of a gas, of a liquid, it actually decreases the solubility of a gas. And I think the best way to demonstrate this is if you take a can of warm soda. We all know if you leave it open, it goes flat. But what does it mean when the soda goes flat? That means that all the gas, the carbon dioxide, escapes. Well, why does it escape? Because it's at a higher temperature, and those gas molecules have a high kinetic energy. They're moving faster, and they escape the container very quickly. How would I slow that down? Cool it off. If I cool that soda, it would go flat much slower. It would take a lot longer to do that. How does pressure affect solubility? Well, one, it only affects gases, and that's another reason why sodas are kept in those airtight cans. They're under pressure, because obviously if you open the can and you hear that sound, you've now released the pressure, and there's really nothing keeping the gas inside the liquid in the soda, so that gas escapes. So the only way to keep that gas in the liquid is to keep it under pressure. So gases, if you increase pressure, you increase solubility. Okay. Let's look at the factors that affect the rate of solution. In other words, not how much dissolves, but how fast something dissolves, and that's a differentiation you should make, right? So this is really not how much dissolves. This is how fast this solute dissolves. Okay. The previous slide is how much dissolves. This is really looking at how fast something dissolves. First thing is what we call surface area, the size of the particles. And we all know this is obvious. The bigger the particles you want to dissolve, the longer it's going to take. So if you increase the surface area, and increasing the surface area literally means breaking the substance into smaller pieces. The best example of this would be if I took a piece of chalk and wanted to put it in, let's say, an acid, there would be a chemical reaction. And we all know that a chalk is a cylinder shape. And literally, surface area would be the part of the chalk that you can actually see by moving it around. That's the surface area. To increase the surface area, I could break it into pieces. If you picture a whole piece of chalk and you look at the amount of surface that you can see, the ends and then the round part, the rounded part, if you break that into two pieces, you now have the additional broken ends there that have surface area. That will make it dissolve faster. Obviously, the fastest way to dissolve it would be to break it into a powder. 2, stirring. Stirring makes things dissolve faster. I think that's pretty much common sense. Again, this doesn't make more dissolve. It only makes it dissolve faster. Also, how much is already dissolved. You know, if you have a lot of sugar dissolved in tea and you try and dissolve more, it might dissolve, but it's going to take a little bit longer. And number 3 is not something I've really ever seen on the Regents exam, so I wouldn't even worry too much about it. Temperature. And I think it's fairly obvious, we talked about this before. Not only does temperature affect how much dissolves, it also affects how fast a solute dissolves. And generally speaking, when you want to dissolve a solid or a liquid, if you increase the temperature, you're increasing how fast it dissolves. In other words, the hotter the water, the faster the solute is going to dissolve. And in gases, it's actually the opposite. The hotter the water, the slower the rate of dissolving. As a matter of fact, you're decreasing not only how fast it dissolves, but the fact that it's going to be able to dissolve less. And I think that that is the end of lesson 2, and we're going to be getting into some math